Hello and welcome to Maths Olympiad Solutions. You've just seen 8 challenging problems from algebra, geometry, number theory, and combinatorics. Whether you tackled them yourself or just want to learn the methods, this video has you covered. Question 1. On algebra, we need to solve the equation. The square root of x plus 6 plus the square root of 4 by 1 equals 7. Step 1. We start by making sure our variable x is valid. It must be greater than or equal to 1/4. Step 2. We isolate one square root and square both sides of the equation. This removes the first square root sign. Step 3. We simplify the equation, then isolate the remaining square root term on one side. Step 4. We square both sides again. This removes the final square root and leaves us with a quadratic equation, 9x. 2. 532x plus 1960 equals 0. Step 5. Solving this quadratic equation gives us two potential answers, x equals 4 and x equals 490 over 9. Step 6. We check these answers in the original equation. We find that x equals 4 works perfectly. The other value, x equals 490 over 9, is an extraneous solution. Question 2. On number theory, we want to find all integers n such that n, 2 plus n plus 1 is divisible by 7. The goal, this means n, 2 plus n plus 1 must be congruent to 0 modulo 7. We only need to test the possible remainders when n is divided by 7, which are the numbers from 0 to 6. The test. We test n equals 12,345 and 6. The results. When n is congruent to 2 mod 7, the expression equals 4 2 plus 1, which is 7. This is divisible by 7. When n is congruent to 4 mod 7, the expression equals 16 4 plus 1, which is 21. This is also divisible by 7. Question 3. On combinatorics, we are selecting a 5-person committee from 8 boys and 6 girls, with the condition that we must include at least 2 girls. The strategy. We calculate the number of ways to form the committee for each possible case that satisfies the condition. 2 girls, 3 girls, 4 girls, or 5 girls. Case 1. 2 girls and 3 boys. We use the combination formula. 6 choose 2 multiplied by 8 choose 3. That is 15 times 56, which equals 840. Case 2. 3 girls and 2 boys. That is 6 choose 3 multiplied by 8 choose 2. That is 20 times 28, which equals 560. Case 3. 4 girls and 1 boy. That is 6 choose 4 multiplied by 8 choose 1. That is 15 times 8, which equals 120. Case 4. 5 girls and 0 boys. That is 6 choose 5 multiplied by 8 choose 0. That is 6 times 1, which equals 6. Question 4. On geometry, we need to find the area of a triangle with side lengths 13, 14, and 15. The method. We use Heron's formula for the area of a triangle when all 3 side lengths are known. Step 1. Calculate the semiperimeter S. This is half the sum of the sides, 13 plus 14 plus 15, divided by 2. The semiperimeter S equals 21. Step 2. Apply Heron's formula. The area equals the square root of S multiplied by SA, SB, and SC. The calculation. We substitute the values. Area equals the square root of 21 times 21 13 times 21 14 times 21 15. This is the square root of 21 times 8 times 7 times 6. The result. By breaking down the numbers and taking out the perfect squares, we find the area is 4 times 21. Question 5. On inequality, we must prove that for all positive real numbers a, b, c, the sum of the fractions a over b plus c, b over a plus c, and c over a plus b is greater than or equal to 3 over 2. The identity. This is a famous result called Nesbitt's inequality. The proof strategy. We use a substitution method based on the denominators. Let x equal b plus c, y equal a plus c, and z equal a plus b. Substitution and simplification. After substituting these values and simplifying the expression, the inequality transforms into a simpler form involving 3 pairs of terms. The key tool, we then apply the arithmetic mean, geometric mean, or MGM, inequality. This states that for any positive number u and v, u over v plus v over u must be greater than or equal to 2. The conclusion, we have 3 such pairs, and since each is greater than or equal to 2, their sum must be greater than or equal to 2 plus 2, which is 6. This confirms the truth of the original inequality. Question 6. On sequences and series, we need to find the sum of the first 100 terms of the sequence of perfect squares 1, 4, 9, 16, and so on. The formula, the sequence is n. 2. The sum of the first n squares has a well-known formula. Is n equals n multiplied by n 1 multiplied by 2n1, all divided by 6. The calculation, for the first 100 terms, n equals 100. S 100 equals 100 times 100 plus 1 times 200 plus 1, all divided by 6. This is 100 times 101 times 201 divided by 6. The simplification, we simplify the expression to 50 times 101 times 67. Question 7. A functional equation. We are looking for all functions f such that fx plus y equals 2fx plus 2fy plus xi. Finding the constant. First, substitute x equals 0 and y equals 0 into the equation. This quickly tells us that f0 must equal 0. Assuming the form, since the right side has a term xi, the solution likely involves a quadratic expression. We assume fx has the form x. 2 plus bx. Comparing terms, we substitute this form into the original equation and compare the coefficients of x, 2, y, 2, xi x, and y on both sides. Solving for constants, by comparing the terms, we find a system of equations equals to a, which suggests a must be 0, but we also have a coefficient for the xi term. A detailed comparison of all terms leads us to the values a equals 1/2 and b equals 1/2. Question 8. On geometry, we are using the power of a point theorem to prove that when chords of and CD intersect at a point P, the product of the segments AP and PB equals the product of the segments CP and PT. The principle, this is the intersecting chords theorem, a special case of the power of a point. The proof method, we use similar triangles, draw the chords AC and DB. The similarity, angle PAC equals angle PDB because they both subtend the same arc. CB, similarly, angle PCA equals angle PBD. Since two angles are equal, the triangles APC and DPB are similar. The conclusion, because the triangles are similar, the ratio of their corresponding sides must be equal. AP over DP equals CP over PB. The result, by cross-multiplying this ratio, we prove the theorem. AP times PB equals CP times PD.